Alright, welcome to Unit 9, Chemical Kinetics. Chemical kinetics studies the rates of chemical reactions, in other words, how fast chemical reactions occur, and we will look at the factors that influence the rate of a chemical reaction in this unit as well. So Lecture 1, Rates of Chemical Reaction, basically deals with some basic ideas of chemical kinetics. What a rate of reaction is, what are some factors that influence the rate at which a chemical reaction takes place, and some other things. So let's get started. Essential questions that need to be addressed for the quiz on this lecture: what is collision theory? What is activation energy? Let's start out with a definition of the rate of a chemical reaction. Essentially, I have a definition written down here that you should put in your notes. The rate of a chemical reaction is the increase in concentration of products or the decrease in concentration of reactants per unit of time. So we're looking at the rate at which concentration is lost per time for the products, for the reactants, or in the case of the products, the amount of concentration that's gained over a period of time. And so what I would definitely have down is this idea of rate of change is equal to the change in concentration per unit of time. If you look at the units then for this, since we're dealing with concentration, we're going to use molar units. And remember, molarity is equal to moles per liter. So we're going to use units with concentration, molarity, moles per liter. And since we're doing rates of reactions as concentration per unit of time, this can be per second. So moles per liter per second will be our units for rate in this particular unit. Another way of addressing the units of rate would be writing moles, liters minus 1 times second minus 1. Basically what we've done is we've taken the reciprocal of the liters and the reciprocal of the seconds, and so that way we can write it out a little bit easier. And so we will use this bottom notation quite a bit when we're dealing with chemical kinetics. So be prepared to see this in the future. Alright. So first of all, what we're going to do is look at this graph. This is a rate graph. Very common in chemical kinetics to see a graph like this. And our question is, according to the graph, what happens to the concentration of the reactant molecules over time? Okay? So, first of all, you're going to have to identify which one of these is the reactant molecules. Is it A or is it B? All right? Now think about what's going to happen to the reactant concentration as a chemical reaction starts taking place. Is the concentration going to decrease over time, or is it going to increase over time? That's right, it should decrease over time. So which one of these curves best represents the molecule concentration decreasing over time? And if you said A, you'd be correct. So as you can see, the concentration is decreasing over time. Alright? So molecules A should be representative of our reactant. And what I would write down here is that we see a decrease in concentration of molecules over time. And so that would answer this question here. Alright? So now, according to the graph, what happens to the concentration of the This should be, according to the graph, let's rewrite this. According to the graph, what happens to the concentration of product? This should be product. Molecules over time. Alright? So we know that molecules A is the reactant, so B must be the product. So what's happening to the concentration of the product over time? Well, it's increasing. So again, I would write down that as a reaction proceeds, the product concentration is going to increase over time. Alright, but let's take a closer look at a few things about this graph and see what we notice. Alright, now if you look at the reactant concentration, it decreases, but eventually it starts leveling out. So at first we see that the reaction is occurring very fast and we're losing reactants quickly, but then over time the amount of reactant molecules begin to disappear, and so the reaction begins to slow down. The same thing we see with the product. At first we create a lot of product, but then as we begin to lose reactant, the amount of product that we make begins to not happen very quickly. So kind of what we see overall from this graph is initially the reaction begins to take place very fast, and then as we begin to run out of reactant molecule, the reaction begins to slow down. Alright, this is common with most reactions. It starts out fast because we have a lot of reactant, but then the reactant molecules begin to disappear because they're changing into product, and so the rate of the reaction slows down. And so I'd write that down in my notes here, those kind of ideas, because they're important to remember. Now, if we go to our next question here, is what is the equation for the slope of the two curved lines? Well, first of all, we have to ask ourselves, what does the slope of these two lines really represent? The slope of these two lines should be equal to the rate of the reaction. Alright, the slope should be the rate. So at any point along these curves, so if you look at the reactants, any point along those curves, we should be able to determine the rate at which the chemical reaction is occurring at the time. And remember, at first the rate is fast, but then as the concentration of the reactants begin to decrease, the rate becomes slow as time goes on, alright? Which we talked about just a minute ago. So what is the equation for the slope of these lines, or in other words, the rate? Well, you can look at it this way. We already know that we're dealing with concentration, which we know is moles per liter, and we're dealing with time, looks like in seconds here. So if we were to put an equation together, we would say that the rate of a reaction is equal to the change in concentration of the reactants over the change in time. Remember, the triangle means change. The brackets that you see here is always going to equal molar concentrations, so moles per liter. Alright, and so we're going to see those brackets a lot in the second half of this year. So again, brackets means molarity or moles per liter, and the triangle is change. So the rate of change for the reactants is going to be a negative slope, so we're going to have to put a negative sign there. Alright, so this is basically the equation for the slope of our reactant molecules. Now what about the products? Well, the products I'm going to erase this a little bit and do the products now. So for the products, we should see the rate is equal to the change, we got to use a triangle, change in concentration of the product over the change, keep on wanting to do brackets, the change in time. Okay, so that would be the slope for the products. And notice the slope is positive, so our rate's going to be positive here, okay, on this equation. So those are the two equations for the reactants and products for those slopes for this graph, okay? So make sure you study these notes very well when it comes to using rate graphs like this in these rate equations, because they're really important to know. Alright? Alright, so let's move on to collision theory. Alright, remember those are one of the essential questions that we need to understand is what is collision theory. Well, essentially what I want you to think about is that all molecules have kinetic energy. Alright, kinetic energy. And because molecules have kinetic energy, they're in constant motion with each other. And once in a while, these molecules are going to interact through collisions. And if they collide, especially if they're reactant molecules, then when these reactant molecules collide, and if they collide successfully, and we'll talk about what the word successfully is here in a minute because it's very important to understand what a successful collision is. But when these molecules collide successfully, then a chemical reaction could take place. And so that's essentially what collision theory really is that in order for a chemical reaction to begin to even occur, reactant molecules must collide successfully with each other. All right? And this is all due to the fact that these molecules have kinetic energy, are in motion. All right? So now let's look at what takes place then really for a chemical reaction. Well, reactant molecules must interact through these successful collisions that we're talking about. Now, if these collisions are successful, then bonds will be broken. The reactant bonds will be broken, and we will then rearrange the atoms to begin to form new bonds. And when we make new bonds, then we will form brand new substances or the products. So this is kind of how a chemical reaction process occurs. One more time, reactant molecules interact through successful collisions, bonds are broken, atoms are then just rearranged, and new bonds will be formed, creating our product. Right? So now we got to look at then what does it mean for successful collisions. So there are two big ideas that determine the rate of a chemical reaction. And these two big ideas are basically based on if collisions will be successful or not. If collisions are successful, a reaction will occur. If they're not successful, no reaction will occur, and so there won't be any rate. And so what we realize is that not all collisions will be successful. So what are the two factors that make them successful? Well, the amount of energy that the reactant molecules collide with and the geometry of those collisions. These are the two important factors that will determine if a chemical reaction will occur and the rate of that reaction. All right? So in order, and this is a really important statement here that I have, is that in order for reactant particles, they must collide with kinetic energy greater than that of what is known as the activation energy. All right? And they have to have the correct geometry. Right? So let me put this in your notes, this statement. Very important statement. Again, in order to react, particles must collide with kinetic energy greater than the activation energy. We'll talk about what activation is in a minute. And they have to have the correct collision geometry, which we'll also talk about. So these two factors are going to determine the rate of a chemical reaction. Okay, so let's talk about the geometry first. Explain what's going on there. Fairly simple idea is that reactant molecules can collide, make many different collisions with different orientations. Okay, collide differently. The collision orientation or the geometry can be crucial in order for the collisions to be successful. All right, so let's kind of draw a diagram here. Let's pretend that we have A and B, and this is a compound A and B, and it's going to react with compound C. Now, compounds or whatever C is, and if C collides in the right way with AB, a reaction could occur. And there's many different places where C could collide with A and B. For instance, maybe C would collide with A. But what we find out is that if C collides with A, no reaction will occur. So it's the wrong collision. Right? But if we find that C collides right in the right place with B, maybe right here, then a reaction will occur. And what will take place is the bond between A and B will be broken, and A will be by itself, leaving us with a new compound of B and C. And now they'll be bonded together. All right? So the right collision angle or orientation must occur in order for the reaction to take place. All right, so now let's look at this all-important concept, the activation energy. And this is what we're going to finish up our lecture on here, is what is activation energy and how does it influence the rate of a chemical reaction. All right, so what I got written down here is kind of the definitions of activation energy. Activation energy, let me get rid of that change. Activation energy is defined as the minimum amount of kinetic energy which particles must have in order for them to react. So activation energy is the energy that's needed to initiate or begin a chemical reaction. So just because molecules collide, and if they even collide in the right orientation, that's great and all, but those collisions must be done with the right amount of kinetic energy. There's a minimum amount of kinetic energy that these molecules must have in order for the reaction to start out with. So again, we go to our important statement that in order for a reaction to occur, particles must collide with kinetic energy greater than the activation energy. Greater than the activation energy. And then the collisions have to have the correct geometry. Alright, so let's look at this little table or diagram here. This guy here is trying to take this rock and from position A, and he's trying to get that rock down to position B. Alright? Well, in order to get that rock from A to B, he has to climb up this hill. Alright? Well, to climb up that hill, he needs some energy to get up that hill. And the energy that is required to get up that hill is known as the activation energy. Alright? Now, once that that guy has enough activation energy to get up to the top of the hill. At the top of the hill is known as the transition state. All right? The transition state is more or less an unstable state that rock is going to be in. All right? So at the top point, that rock could either go down to B or it could go back down to A. And so it has a decision to make. Do I go to A or do I go to B once it's at that transition state? Well, if it goes to B, the energy difference between A and B is pretty significant. All right? So if I was to draw a line here, you'd probably recognize that it would look like something like this. Actually, let me redraw this a little bit. You've seen these diagrams before, where you start out with reactant and then you find product. So this is A and B, and the difference between A and B is delta H, or the amount of energy released. All right? And so going through from the transition state to down to B is going to release a lot of energy. And that energy is going to be at a minimal amount of energy, which will be favorable. So I'd rather go to B than A, because if it goes back to A, then it only loses a little bit of energy. All right? So think about that. That's the thermodynamics in all of this. But the kinetics is going to be the energy required to get up to that transition state. This stuff right here. This energy barrier. And that energy barrier to get to that transition state is the activation energy. And so when molecules collide, they need enough energy to overcome this activation barrier, in other words, this big hill, in order to get to the transition state. Alright, so let's look a little bit closer at this. You can see below here some energy diagrams here. Now, instead of calling these the activated complex, we're not going to use that terminology in this class. Instead, we're going to use the transition state. So again, up of our top point there is known as the transition state. So we're going to start out with a reaction with A and B. Those are our reactants. Now A and B, you're going to have to visualize this. A and B have to collide with each other. Alright? And they have to collide with successfully. So the first thing that has to take place is they must collide with the right geometrical orientation. Alright? Now, if they do so, then those collisions also have to have enough energy. Okay? Again, that energy is called the activation energy. Alright? That energy of activation is needed in order to get those reactant molecules to the transition state. Now, the transition state is quite unstable. Okay? So the activation energy to complete the unstable transition state, which I have written there. Alright? That transition state will not form unless there's enough energy to stabilize it. So this is known as an energy barrier. Or in other words, you can look at the activation energy as a barrier. And that's this barrier right here. Alright? And so a lot of times we'll refer activation energy to the symbol EA. Energy of activation. Right? Every reaction has an energy barrier, or a certain amount of energy needed to get to that transition state in a reaction. And so you can look at these two reactions and they're a little bit different. In the first one, the energy barrier or the activation energy needed is small. But look at the other reaction here. It has a larger energy barrier that it must overcome. So this needs a large activation energy, and the other one is just a smaller amount amount of activation energy in order to start the reaction that occurs between these reactants and products. All right. So what I want to do here is summarize and put this all together. Okay. Collision theory is the idea that reactant molecules must collide successfully with each other to initiate a chemical reaction. The successful collisions are that the reactant molecules collide with A, the right geometrical angles, so the right orientation, and B, the reactant molecules must collide with enough energy to overcome the activation state energy barrier to make the transition state. All right? And once that transition state is formed, then the reactants can form our products, which is C and D here. All right? C and D. All right? And that's pretty much the basics behind kinetics and the beginning stages of understanding the rates at which a chemical reaction is going to occur. And so that is really it for this lecture. So what I want you to do is go back and study these notes very carefully so that when you come into class that you're able to take a quiz on this material, as well as that in the next lecture you can apply this material to lecture 2, which is important. All right, so that is it for this particular lecture.